Welcome back. Tonight we are going to explore nth root and rational exponents, which is an extension of simplifying radicals that we did today. So to get started, you do have a notes packet, but I would like you to just sit back, relax, and enjoy the show. So while you're sitting back and relaxing, I actually need your full attention, and I do need you to concentrate. The mechanics of this are not actually that difficult, but I would like you to challenge yourself to understand all of the reasons behind why it works. So stick with me and let's get started. Evaluating nth roots. So that is not just a square root, we can extend the concept of a square root to other types of roots. 2 is a cube root of 8. That's because 2 to the third equals 8. So if I take the third root of 8, it would be 2. 3 is a fourth root of 81 because 3 to the fourth equals 81. So in general, for any integer n greater than 1, if b to the n equals a, then b is the nth root of a. So look at the diagram, okay? An nth root is written like this, that's the index, and b would be the nth root of a. So if you really focus on this picture down here, that first statement or the middle statement would make sense. b is the nth root of a. So 3 is the fourth root of 81. 2 is the third root of 8, etc. Got it? Think about that and make sure you understand that. Evaluating nth roots. We can write an nth root as a power of a, just like we saw in the last slide. For the particular case of a square root, we suppose that in this case we don't write the index. We know that that's a 2. And we're going to call that a to the k. We can determine a value for k as follows. So try to pay attention here, okay? This is an algebraic proof, and it is in your notes, but I really right now just want you to watch this and understand we've done a little bit of these algebraic proofs, so I want you to stay with me here. In the first case, the square root of a times the square root of a is a. That's the definition of a square root. Now I'm just going to substitute a to the k, which we defined up here as being the square root of a, for k. So that's just substitution. They're going to pop that little square root there. Now, we know this is true. We learned this last year. If we have the same base raised to a power, we just add the powers. So this is something that's a little new, and you'll do more of this in Algebra 2. But when the bases are equal, you can also set the exponents equal. So 2 to the k would equal 1, and k equals 1/2. A square root is the same as raising it to the power of 1/2. So we can likewise do a similar proof for any of the other roots, and we're going to find that they are fractional exponents. So a to the 1/3 means the cube root of a to the 1/4 means the fourth root of a, and in general a to the 1 over n for any integer n greater than 1 is going to be the nth root of a. Now think about this. Let n be an integer greater than 1 and a be a real number. Okay, so we're not talking about I here. If n is odd, then a has 1 real nth root. So if this is an odd index, you're only going to have 1 real root. If n is even and a is greater than 0, then a has 2 real roots. So the square root, the fourth root, the sixth root, you're going to have 2 possibilities there, because remember, when you square a negative number, it's going to drop out. So that's why you're going to get an extra root. If n is even as a equals 0, then it's just going to be 0. And if n is even and a is less than 0, then a has no real nth roots, because that's where you get into the situation of complex numbers with I. Okay, so how do I find them? Find the indicated real root of a. Well, if n is 3 and a is negative 125, because 3 is an odd number and a is negative 125, it would have 1 real cube root, because negative 5 to the third is negative 125. We could also write it, the cubed root of negative 125 is negative 5, or negative 125 to the 1/3 equals negative 5. Finding nth roots when n is 4 and a is 16. So I'm going to take the fourth root of 16. It's even, so, and 16 is greater than 0, so I'm going to have 2 real fourth roots. And that's going to be 2 or negative 2. So the fourth root of 16 is going to be positive or negative 2, or 16 to the 1/4 is going to be, I don't know why that went so fast, 16 to the 1/4 is going to be positive or negative 2. A rational exponent does not have to be of the form 1 over n. Here's where it gets a little complicated. So n is an integer greater than 1. Other rational numbers, you can have 3/2, -1/2, etc. And this is what we're going to practice more of tonight. If 1 over n is the nth root of a and m is a positive integer, we can just write this m over n as the nth root of a to the m power. And with negative exponents, remember, you just do the same thing but make it a fraction. Okay. So if I want to take this example and write it using radical notation, it's just the square root of 9 to the third, or the square root of 9 raised to the third power. It is commutative, okay? So that's just going to be 27 no matter which way I do that. 32 to the negative 2/5, it's 1 over 32 to the 2/5, which means I'm going to take the fifth root of 32 and square it. You don't really want to take the fifth root of 32 squared. It's just more complicated. It's simpler if you can do this part to do it first. Okay? So we're going to get some practice now, so you can go ahead and take out your notes. So please turn to this page, which follows most of the work we did today in class. And I just want to say at this point that if you really followed what I was doing just now and it makes total sense to you, you don't have to stay with me here. You can either fast forward or just go and check the answer key, because I'm going to kind of go slow, and I know for some of you, you don't like the longer videos. So I'm going to kind of work through a lot of these problems for students that are having issues, but if you get it, feel free to cut me off at any point. I won't be offended. Okay, so the top part of it just shows you what we just did in the PowerPoint. And if I wanted to rewrite these, at these a's, it would be a to the 1/2, a to the 1/3, a to the 1/4, and a to the 1/6. So we could go ahead, and I'm just going to leave that first one for you because that's pretty basic. The second one is pretty basic. It's just like above. The third one is where it starts to get interesting, and this is kind of our baby step here. So this is the same as x to the 1/3 squared. So if I want to rewrite that, I'm going to write it as x to the 2/3. Okay? Or I could have said here, actually, if you look at that more closely, x squared to the 1/3. Either way, again, it's like multiplication, so it's commutative. So go ahead and pause here and check out the next three on your own. I got x to the 4/7, y to the 5/2. And be sure to use parentheses here, okay? Because it's going to make a huge difference when and when not to use parentheses. This is y times z to the 6/11. Now, you could put that z to the 6/11 in parentheses if you chose, but remember that the exponent only applies to who it's sitting on. If it's sitting on a parenthesis, such as this one, then it applies to everything in the parenthesis. In this case, there are no parentheses. It's sitting on z, so it only applies to z. Rewrite using radical notation. So now I'm going to do this using the radical notation. So this is going to be the fourth root of x cubed. This is going to be the fifth root of x to the 6. If you kind of get the hang of it, you can pause here and do the rest on your own. So this is 5. Now remember, the 1/2 only applies to the x, so times the square root of x. That 5 is not raised to the 1/2, such as in the next case where it is raised to the 1/2. So this is the square root of 5x. I hope you really see the distinction there between C and D. Very different. Okay, so this is xz to the negative 4/3. So that's 1 over xz to the 4/3, which is the same as 1 over xz, the cubed root of xz, and I'm going to put this whole thing to the 4th. You could put the 4th inside too. So 32, let's evaluate this one. 1 over 32 to the 2/5. Well, the fifth root of 32 is 2, but let's say we didn't know that. We would just write the fifth root of 32. And if I put this squared in there, then I want to square it. I don't really want to do that. I'd rather take the fifth root of 32 and then square it, which is 1 over 2 squared, which is 4. Final answer. And this just repeats what you saw in the earlier slides. A lot of rules here, a lot of properties. I'm not going to actually explain them, but I will do the examples because some of them get a little bit crazy. So remember that when we multiply like bases, we add the exponents. Well, that works out kind of nice in this case because 3/2 plus 1/2 is 4/2, which is 3 squared, which is 9. So if you think you understood that one, our rules didn't change. That's the nice thing about math. If you have a rule, it's pretty strong. It works for everything. It's not like English where I before E, except after C, and then except in, blah, blah, blah. If it's a rule, it's a rule. It works all the time. So division of powers with the same base says I subtract the exponents. So 5/2 minus 1/2 is going to give me 4 again to the 4/2, which is going to give me 16. So our rules are our rules. So raising a power to a power, I multiply the exponents. -2 to the 3/2 squared. Those 2's are going to cancel, and that's going to give me -2 to the 3rd power, which is going to give me -8. And in the case of the next one, again, the 3 multiplied by 5/3 cancels, so I get 4 to the 5th. And I can just leave that way. Okay, so in the next case, distribution over multiplication. So that's saying that this is kind of like 4 to the 1/2 x to the 1/2, or the whole thing, take the square root of 4x. Okay, what this is saying is really you could do 4 to the 1/2 times x to the 1/2. So that's going to, either way, it's going to give you 2 square root of x. Cube root, distribution over division, so I could do the cube root of 8 over the cube root of 27. So that's going to be the same as the cube root of 8 over 27, but I don't want to do it that way because it doesn't work out, so I'm going to do 2 over 3. You can do it however it works out, basically, is what it's saying. Negative exponents, everybody's favorite, right? It doesn't change. It's 1 over whatever. That's what you want to do. So 25 to the negative 1/2 is going to be 1 over 25 to the 1/2. You kind of just got to go on autopilot as far as that's concerned, and that's 1/5. Okay? I'm not going to go through all of those. Well, maybe I'll do the third one there because that's a little yucky. So this is the same as 4 times 8 to the 2/3. Remember, if it's a negative exponent in the denominator, then it's going to move up to the numerator. And the cube root of 8 is 2. 2 squared 4. 4 times 4, 16. And hopefully you followed that. I can take the nth root, square root, whatever the case is, of each individually, or I can do it all together, whatever works for me. That's what the next one's saying. So I want to take the cube root of 8 and the cube root of 3. Well, the cube root of 3, I can't do that. I could take the cube root of 24, but that's not going to help me either. So I'm going to do 2 times the cube root of 3. And then the next one is saying I can do the quotient as a whole or individually. Well, cube root of 16 doesn't really work out, and cube root of 2 doesn't work out, but cube root of 8 works out. So why wouldn't I do that? It makes it a lot easier. So you can definitely pause here and just come back and check your answers. I will do a couple of the nasty ones, and I will also post an answer key. Okay? All right. Let's take a look at 64 to the negative 2/3. It looks bad, but just make it 1 over 64 to the 2/3. Now, do we want to square 64 and then take the cube root of that? I don't think so. I think I want to take the cube root of 64 and then square it, because I know the cube root of 64 is 4. So that's 1 over 4 squared, which is 1/16. Final answer for that one. Let's see, 1 over 64 to the negative 2/3 is going to be the same as 64 to the 2/3, which we just kind of did. So it's going to be 16 instead of negative 16. All right? How about 7 over 7 to the 1/3? Well, that's 7 to the 1st over 7 to the 1/3, so 1 minus 1/3 using our quotient rule, and that's 7 to the 2/3. And there's really not much I can do. I can write it in either form as long as I'm not directed. Okay? The one below it's kind of interesting because I can't do the cubed root of 25 or the cubed root of 5, but I can do the cubed root of 125. It's 5. So try to simplify them if you can. Don't say I can't do that, because you can do that. I might use my power rule here, because that's going to give me 4. If I apply this to this and this to this power, then I would get 4 to the negative 1 times 2 to the negative 1. Well, that's 1/4 times 1/2, which is 1/8. Really not too bad. Okay? I could change that to make them like bases. So that's 2 squared to the 3rd, which is the same as 2 to the 6th times 2 to the 3rd to the negative 1/3. So that's 2 to the 9th to the negative 1/3. So it's 2 to the negative 3, which is also 1/8. So either way you do that, it works out. And then this one, it looks worse than it is. It's 12 to the, well, actually, I'm going to do that. Yeah, the cubed root of 12 over the cubed root of 4 is going to give me the cubed root of 3 squared. And this whole thing was squared. So that's going to be the cubed root of 9, which we don't know. Irrational. Okay? So you should pretty much be set with those, and I'll see you tomorrow. We'll practice a lot of these tomorrow. So don't feel too confused. We're going to do a lot of practice tomorrow. Have a great night.